The trapezium rule is one of the simpler rules of quadrature, so let's take a look at how that is defined. Essentially, what we're trying to do, as always, is we're trying to find the numeric value of some integral. So essentially, we have some function maybe going like this, and we want to find an integral between 2 points a and b. Let's mark them like so. And what we do is we subdivide the integral into several strips. So what we're basically saying is we're going to evenly divide the range between a and b into several strips, and then we're going to evaluate the strips using some simplified procedure. So the trapezium rule is probably the simplest procedure there is, actually. So once you arrive at the subdivisions, what you do essentially is you connect the endpoints. So you say, let's just connect the function points and evaluate the areas of the trapezium. So you connect these 2 points and these 2 points and these 2 points and these 2 points, and you take each of the trapezium, you calculate the area, and you simply add them up. That's all there is to it. So essentially what we're doing as a kind of approximation of the integral is we're saying that some integral going from x at index k to x at index k plus 1 is actually being estimated as the area of the trapezium, which is h over 2, where h is this distance, so we'll call it h, and it's this distance over 2 multiplied by the sum of the function values, so it's f at k plus f at k plus 1, because that's the formula for the area of a trapezium. So essentially what we can do, and I'm not going to show it here, but we can show that the error in calculating the trapezium compared to a function, for example, is somewhere on the order of the following: minus h cubed multiplied by the second derivative of the function at some point c divided by 12, where c is between those 2 points. So c is between some 2 points, xk and xk plus 1. So this is the error estimate for a single trapezium whose area is being calculated. Of course, we want to sum several of them up. So what we're essentially saying is that the integral going from a to b of some function f of x dx is actually a sum of these little integrals. So a sum from x0 to x1 of the integral plus the sum from x1 to x2 of, once again, that same integral, and all the way up to the sum, or the integral of xn minus 1 to xn f of x dx, assuming that we're subdividing everything into n separate strips. So essentially we can rewrite this in terms of our estimates using the trapezium rule. So we have this formula with h over 2 here, h over 2 of the two function values on either side. So we can essentially say that this is h over 2 of f0 plus f1 plus h over 2 f1 plus f2, and so on all the way up to h over 2 fn minus 1 plus fn. So essentially what we can do with this is we can rewrite it, because you'll notice that some of the terms are duplicated here. So you have f1 here, you have f2 here, and f2 here, and all the way up to fn minus 1, which will be here and here, but there's only one f0, there's only one f of n. So essentially, all those two terms, when they divided by 2, they just left with h. So we may as well divide f0 and fn by 2 as well. So this all simplifies to the following. So you multiply h by f0 over 2 plus f1 plus f2, and all the way up to fn minus 1 plus fn over 2. So that's the trapezium rule with the application of the actual formula, and we can also estimate the error similarly. So the error is based on the error that we have for the individual strip, the error that I've mentioned here. And essentially, let's just write this down. I'm not going to do the workings for the error. So the error here is minus b minus a multiplied by the multiplied actually first of all by the distance between the points squared multiplied by h squared, then times the second derivative at some point c divided by 12, where c is somewhere between a and b. So that's our error term. Let's take a look at an example of actually applying this procedure to evaluate some integral. So we're going to calculate a reasonably simple integral, the integral of, well, let's have 1 over x. So let's have an example. Okay, and what we're trying to do is we're trying to calculate the integral of 1 over x dx from, let's say, 1.3 to 1.4, and we're actually going to not even consider subdivision. We're just going to consider the points 1.3 and 1.4, meaning that, you know, if you have a function going like this, then all you're doing is, instead of evaluating the actual area under the curve here, you're basically drawing a trapezium like this, and you're calculating the area of the trapezium, and you're saying, well, this is an estimate of some kind. So let's see how it goes for this particular approach. So what we're essentially saying is that we're taking the value of h to be equal to 0.1. That's the distance between the left point and the right point, between 1.3 and 1.4. So we have the h value, which is 0.1, and then we apply the formula that we had up above here. So essentially we say that, oh, let's just divide it by 2 and multiply it by the sum of the functions at those points. So we plug in 1.3 in here, we plug in 1.4 here, we get 1 over 1.3 plus 1 over 1.4, and we get the value of 0.07418. Okay, so we can also calculate the error, because we can take the derivative. So the first derivative of x is equal to minus 1 over x squared, and the second derivative of the function is equal to 2 over x cubed. So essentially we can basically plug in the second derivative in here and calculate those values. So the error, let's just calculate the error. Error is going to be equal to minus, and then b minus a is minus, well, it's 0.1, but it's also multiplied by h squared, which is also 0.1 squared. So that's 0.1 times 0.1 squared, that's 0.1 cubed. And then it's divided by 12, and then we have 2 over c cubed. And let me explain where this comes from, because on top we have the second derivative at c, but the second derivative is actually 2 over x cubed. So essentially it's this term that's being kind of replicated here with the value of c replacing the value of x. And of course we have this requirement that c is somewhere between a and b. So in our case, c is somewhere between 1.3 and 1.4. If we want to maximize the error, if we want the maximum value, then we have to take c being equal to 1.3, in which case the error is going to be equal to somewhere around 8 by 10 to the minus 5. So if we now calculate the integral using something like MATLAB, for example, so if we actually get the value of the integral to within some precision, let's say 5 decimal places, we would get 0.07411. So if you look at the estimate that we got, which is this value, and if you look at the actual value, you'll see that the difference is actually 7 by 10 to the minus 5, whereas our estimate is 8 by 10 to the minus 5, so it's a pretty good estimate of the actual error.